Can everybody hear me? Okay. Right. Just a second. And we're off. So I don't know if you have had a chance to have a look at the problems. So I've tried my best to put them earlier this time. And so who has done, have you done simple harmonic motion at school? Yes or no? Simple harmonic motion. No, yes, no, no. Okay. So mostly no's. Right. Okay, then I'll talk you through about simple harmonic motion a bit, just the general stuff, and then we'll get to do some problems. Okay, so here's my screen. So let's just define simple harmonic motion. If you could imagine a mass on a spring, and let's say the mass is on the floor, there is a spring. If you pull this spring, if you pull the mass, let's say to the right, and let go, it will start oscillating. It will bounce left and right effectively. And when the force is to the right of the equilibrium position, the spring will attempt to return it back to the equilibrium position. And when the mass is to the left of the equilibrium position, the spring will push it back to the equilibrium position. So you have a system where the force is always trying to return it to the equilibrium. And this is where oscillations happen. Yeah, so oscillations are incredibly important in physics. It's one of the most important topics, one of the most interesting topics, of course. And it's kind of my pleasure to introduce you to it. So if you remember, you should know Hooke's law. So if the spring constant K is extended by, if we move the mass to the right, so let's say this is the equilibrium position, and this is the new position X. Then the restoring force is minus Kx, spring constant times the extension. Now, we know that force is mass times acceleration. Mass times acceleration. And minus Kx. But we also know that acceleration is the second derivative. We know that the acceleration is the derivative of speed, dv dt, but speed is the derivative of x. So it's equal to d over dt, dx dt. Because speed, yeah, v is the derivative of x. In other words, the acceleration is the second derivative of the displacement with respect to time. And in physics, we have a special notation. We say x double dot. X double dot means second derivative. So speed is the first derivative of, so the notation means derivative with respect to time. And of course, acceleration is the first derivative of velocity. Okay, right. So we can replace A with x double dot. Double dot is equal to minus kx. What we aim to find is the equation of x with respect to time. So we want to know what is the position of the mass at any given time. Does everything I said so far make sense? Can you please tell me on a scale of 0 to 10? Is everything so far? Okay. We are aiming to, as I said, we are aiming to find x with respect to time. So the position of x, so we want to be able to predict where the mass will be at any given moment in time. This is called the equation of motion. And the equation of motion is x, and this is a differential equation. This is a differential equation. So we're going to rewrite it. We're going to say x double dot is equal to minus k over m x. Now, k over m is a positive constant. So for convenience, and nothing else yet, we replace it. X double dot is equal to minus omega squared x, where omega is a constant, and omega squared is obviously a positive constant because a squared number cannot be negative, where omega squared is a positive constant. Positive constant. Okay, so we have this equation. Well, it's difficult to solve it. I mean, unless you are very good at second order differential equations. Minus omega squared x. We can guess a solution. We can try to guess a solution. So the question is, what is x? Is x. Now, let's see. Well, it says that the second derivative of x is minus a constant times x itself. What would be a good candidate for x? Which function? Yeah, sine. So we know that the second derivative of sine is minus sine. Yes, so derivative of sine is cosine, and derivative of cosine is minus sine. So sine is a very good candidate. So my guess, well, it's an educated guess, of course, because I've done this many times, guess that x is a constant multiplied by sine omega t. Omega t. Omega is a constant, is a constant, so that makes sense. So this first derivative is use the chain rule here. It's a multiplied by omega multiplied by cosine omega t. Now the second derivative, now it's derivative of cosine, and it's another chain rule. So it's minus a omega squared sine omega t. And let's substitute. So sub into x double dot equals minus omega squared x. And we have minus a omega squared sine omega t equals minus omega squared a sine omega t. It's the same thing. it works. That means x equals a sine omega t is a solution. X equals a sine omega t is a solution. What does this function look like? Well, it's a sine graph. So obviously it looks like this. And so this is time. This is x. X is the position of the mass. And it looks something like this. So this is a, this is minus a, and the time period. Well, if you know the properties of the sine function, the time period is 2 pi divided by the constant in front of t. So it's 2 pi over omega. So this point is 2 pi over omega. And omega has a special name. Omega is called the angular frequency. Omega is the angular frequency. Its link with regular frequency is that omega is equal to 2 pi times f, where f is the frequency of oscillations. And it makes perfect sense that if an object is released, it will oscillate, it will vibrate left and right, left and right. And we need a definition of simple harmonic motion. Definition. If the restoring force is proportional to displacement and has an opposite direction to displacement, the object will perform simple harmonic motion. I'm kind of creating the definition on the fly. I mean, there's a much more refined definition in the assignment. The restoring force is proportional to the displacement. So in other words, if you draw a graph of the restoring force, or the force that is trying to return the mass back to its original position. So this is F, this is displacement, X. The graph looks like this. This is the maximum displacement. We call it amplitude, minus A, the amplitude. And here is plus A. So yes, A is amplitude. Okay, this is the maximum restoring force. Well, it's minimum restoring force, depending on how you look at it. You could say it's also maximum, maximum by modulus. Now, even though this is a solution, it's not the only solution. It's not the only solution of the equation. For example, x equals b multiplied by cos omega t is also a solution. So if only we could have a general solution, A general solution is um, that describes any motion. Because what is the difference? Because this solution that we've drawn here assumes that the object is in the equilibrium position when t is 0. When t is 0, the solution. But there are many different ways we can establish simple harmonic motion. We could pull it back and release, or we can kick it and it starts vibrating, or we can kick it but not from the equilibrium position. So there are many ways how an object can vibrate. And to account for that, we have another equation, which is called the general solution. And this is one of the way how to write the general solution. And the first task is to establish that this is in fact a solution to that. So how do you do that? How do you prove that this is a solution to this equation? Somebody help me. How do you show that? Yeah, you plug it into here. And to do that, I need to find the second derivative first. So I find the first derivative, and that's a omega cos omega t plus phi. Phi is a constant. Okay. And the second derivative, so omega is the constant, so it's minus a omega squared sine omega t plus phi. Good. And we can see that in fact, yeah, it works. We plug it in, and it works. So plug in x equals minus omega squared x. So we get minus a omega squared sine omega t plus phi equals minus a omega squared sine, omega t plus phi. Right. Computer is not responding quick enough for my writing. And it works. So it is a solution. Works. Now phi is called the phase of oscillation. It might be a little bit overwhelming at this point, and especially phase is not really discussed in the A-level program, although it is a very important concept. Phase phi determines the initial position, the initial initial conditions. We call it initial conditions of the oscillator. So if the oscillator starts from maximum positive displacement, basically that. So what does that mean? If t is 0, the maximum displacement is a. X is a. And we use that to find phi. We do a equals a sine omega times 0 plus phi. And from here, we see that sine phi is 1, of course, because we cancel that. Sine phi is 1, and phi is, Well, in fact, there are many different solutions. It doesn't really matter which one you choose. Any solution. So the easiest one is pi over 2. Okay, so the equation will be x equals a sine omega t plus pi over 2. This is the equation if you start from the maximum position. So you let go, it starts moving backwards immediately. So it looks like this. So x, t, we start in the maximum position, and then we go like this. The oscillator starts from the equilibrium position in B. That means that if t is 0, displacement is 0. And of course, so 0 equals a multiplied by sine omega times 0 plus phi. So sine phi is 0. Sine phi is 0. There are two solutions. Phi is 0 or phi is pi. So what's the difference? Well, if you start the oscillator from the equilibrium position, there are two possibilities. This is the mass. You can start, this is the equilibrium position. You can kick it to the right, or you can kick it to the left. In both cases, you start from the middle, just different ways to start. Any questions? Please ask me. Please ask me if it's overwhelming. So how are you finding it so far? So 0 is very sorry, 0 is very difficult, 10 is very easy. Can you vote please in the chat? 0 is very difficult, 10 is easy. Sorry, it's the other way around. So 9, easy. Okay, so we're kind of mostly doing maths at this point, little physics. Now, how to do the most typical problem is to find the time period of oscillation. And one of the for a spring mass system. So what's the approach? I'll put it in a separate box because it's kind of a big deal. Finding the time period, because that's the most common question. Finding the time period of an oscillator later. Let's say you have a spring, a mass on a spring. The mass is m, the spring constant is k. If you displace the mass by x to the right, So this is the equilibrium position, 0, and this is x. The restoring force, as we already established, is minus kx. So we write down that the resultant force, or the restoring, well, in this case, restoring force and resultant force are the same thing, is minus kx, or ma equals minus kx. That means acceleration is minus k over m times x. Now we know the equation of SHM, equation of SHM is A equals minus omega squared x, or x double dot is minus omega squared x. It's the same thing, so it doesn't really matter which way you write. Now, all we need to do is compare these two equations. Compare these two equations, and we see that omega squared is k over m. That means that omega is square root of k over m. And we know that time period is 2 pi divided by omega, and that's 2 pi square root of m over k. So in other words, the time period of a spring mass system is 2 pi square root m over k. And it kind of makes sense. If you increase the mass, the time period will increase. If you make the spring stiffer, if you make it if you make a stiffer spring, the time period will decrease. It will vibrate faster. So the equation makes sense. In a similar way, another oscillator, I don't think I'll prove this. It's proved in the assignment. If you have a pendulum of length L, the time period of the pendulum is 2 pi square root L over G. 2 pi square root L over G. This is the time period of a pendulum. And you can see that the time period of a pendulum only depends on one thing. It depends on the length of the pendulum and does not depend on the mass of the pendulum. So any pendulum, so any mass on a rope will oscillate back and forth with the time period, which is directly proportional to the square root of L. Okay. But the strategy, and I will do this several times today, the strategy to find the time period is this. You displace the mass by a small amount. You look at the forces involved. You write down Newton's second law, because this is Newton's second law. And from there, you compare the resulting equation with the original equation, and you find omega. And finding omega allows you to find t. Does this make sense? On a scale of 0 to 10, please. Nice. Okay. Right. And we will do this. Yeah, let's do this. A mass, when hung stationary by a spring, extends the spring by delta L. Find the period of oscillations of the mass on the spring. Well, we kind of know the formula, and we know that to do this, we need to find m and we need to find k. So how are we going to do this is if the only thing that is given is delta L. Well, let's find a period of oscillations of the vertical oscillations. I forgot the word for vertical, of course, vertical, because it can also swing. Yeah, it can also swing. But yes, vertical. So first we take the mass and we hang it from a spring. We hang it from a spring. And when the spring is unloaded, let's say the length is L0. When the spring is loaded with the mass, it becomes L0 plus delta L. And from here we can write Newton's first law here. Newton's first law. So there's a downwards force, which is mg, and there's an upwards force of k delta L. K delta L, because the delta L is the extension. So let's write this down. Mg is k delta L. Okay. Now let's say we move the spring even further. We move the spring even further. So look, there's a short way of doing it. Short way. Short way of doing it. And the short way of doing it is saying, well, we know the time period. It's 2 pi square root of m over k. And m over k we can establish from here. M over k is the same as delta L over G. So the answer is 2 pi square root delta L over G. That's the solution, the short solution. I do want to show you how to do it properly, because it's not always that you're given a single mass on a spring or even a single spring. So what are we interested in? We assume that we move the spring even further down. This is the equilibrium position. Equilibrium. And we move the mass down. So we pull the mass down, and we are looking at the forces acting on the mass. And of course, there's going to be an upwards force. There's going to be a gravitational force down, mg. There is the upwards force of k delta kx, and there's another upward force of k delta L. Well, I mean, you could say it's k times x plus delta L, the total extension. So we write down Newton's second law. So mass acceleration is equal to, so acceleration is displacement is down. So this is x, this is 0. So this is the positive direction, positive x-axis. So ma equals minus kx minus k delta L plus mg. But from here, we've learned that mg is k delta L, so these cancel out. So we have ma equals minus kx, and acceleration is minus k over mx. And we remember that acceleration is minus omega squared x. So from here, we deduce that omega squared is k over m, and then do the same thing. So time period is 2 pi over omega, which is 2 pi multiplied by m over k. And m over k, as we already established, is 2 pi delta L over g. Okay. So interestingly, that the time period of a spring mass system has this almost the same equation as the period of a pendulum. That's quite interesting. Right. Now, I'll just continue practicing, showing you how to solve it. Now, we again here, what do? We direct the x-axis. We mark the equilibrium position, 0. We displace the mass by a small amount, x. Once it's displaced, we write down Newton's second law. So Newton's second law for A, that mass acceleration is going to be, so both springs are stretched. So we have a force, both springs are stretched by the same amount. So we have minus k1x minus k2x. So we simplify that. Ma equals minus k1 plus k2x. And from here, acceleration is minus k1 plus k2 over mx. We compare it to the equation omega squared x, and we see that omega squared is k1 plus k2 over m, and of course the time period is 2 pi over omega, which is 2 pi square root 2 pi, so m over k1 plus k2 time period. Go to question B. Question B is slightly harder. So the same idea. This is 0. Displace the mass by x. Now, the force in the both springs will be the same. Force in the both springs will be the same, but the extensions of the springs will be different. So let's say that this spring has extended by x1, and this spring has extended by x2. And of course, we know that x1 plus x2 is x, is the total displacement. Now, we also know that the force is the same. So K1 x1 has to be the same as K2 x2. Well, it's it could be a bit of a handful here, but let's see the easiest way to do it. Well, we express x1 as k2 over k1, x2, and we plug it into here. So we get k2 over k1, x2 plus x2 equals x. In other words, x is equal to x2 multiplied by k1 plus k2 over k1, and x2 is equal to k1 x divided by k1x over k1 plus k2. In a similar way, it's easy to prove that x1, it comes from symmetry, is k2 multiplied by x over k1 plus k2. So F, oh, of course, sorry. I didn't really need that. So F is equal to K, so the force is minus K1 x1, right? Because the force is the same, force inverse. So mass acceleration is equal to minus K1 x1. You might as well just say it's equal to minus K2 x2. And here, so minus K1 x1, we put in x1 from here. So mass acceleration is equal to minus K1 multiplied by K2 x divided by K1 plus K2. And we get acceleration is equal to minus K1, K2 mass K1 plus K2 x. And from here, we can find that that's t. That's the time period of A, and the time period of B, the second oscillator, is equal to, so it's going to be 2 pi square root of m k1 plus k2 divided by k1, k2. Right. Hope that makes sense. Now TC, now interestingly enough, this is when we say springs are in parallel, and you will have a very similar question in the assignment. Springs in parallel. This is springs in series. Now C, is C series or parallel? What do you think? Is C series or parallel? It kind of looks neither, but in fact, it's the same thing as parallel springs. So how does that work? Well, if you move the mass to the right, you will see that this spring produces a force to the left, but this spring also produces a force to the left. And the total force to the left is K1x and plus K2x. I'll leave it at that. I'm just saying that this A is equivalent to C. And I would like you to prove it by yourself. This is the same as this. There's no difference whatsoever whether you have two springs in parallel or two springs like this. I would call this a parallel connection as well. These are two springs in parallel. And I use some formula. So springs in series, in springs in parallel, the total K is equal to K1 plus K2. Springs in series, parallel, series 1 over K total. This is the total 1 over K1, K2. Looks familiar, doesn't it? Parallel connection, series connection. It's just the other way around if you're talking about resistors. Right. How much time do we have? We have some amazing questions here. Okay, I'll try to do this quickly. Now, one more thing that you will see is the relationship between the potential energy and the time period. And just give me a moment. Okay. Find a ball radius r slides in a trough of radius r. So here we can see that if the ball rolls up, the normal force will return it to the original position. So if we let go of the ball will oscillate as it does. Okay, so find the relationship between small displacement x and the potential energy of the ball. So what potential energy are we talking about? Somebody help me. What do we mean by the potential energy of the ball? Well, which potential energy are we talking about? Yeah, of course, GPE. Yeah, if you displace the ball a small amount, small distance, the ball will raise. The ball will raise. We're talking about small oscillations, and you will see in a minute why. So let's say the ball has displaced here. Now this is a bit tricky because we need to consider the center of the ball rather than the bottom of the ball. We need to find the displacement of the center, and this radius is going to be r minus r. And if we draw a line like this, so this angle is theta. This is r minus r, and so the height, which it is raised, height is going to be r minus r, minus R minus R cosine theta. How did I establish that? Well, this, if this is R minus R, this is R minus R cos theta. Okay, and this is yeah. Now this displacement we will call X. This is a small displacement of the ball X. And we know that X is R minus R sine theta. Sine theta. So when the, yes. And because we're talking about small displacements, we know that sine theta is approximately equal to theta. So this is approximately R minus R theta. So from here, theta is X divided by R minus R. Now, we want the gravitational potential energy. To do the gravitational potential energy, we of course need H. And to do H, we need theta. So H is equal to R minus R. I'll take this out of the brackets, and we're left with 1 minus cos theta. We need to use the small angular approximation for cosine as well. So cosine theta is approximately 1 minus theta squared over 2. This is a small angular approximation formula for cosine. And we place that here. So we get R minus R, 1 minus 1 plus theta squared over 2. And that is R minus R, theta squared over 2, which is R minus R, theta squared, so that's X squared over R minus R squared times 2. In other words, H is X squared over R minus R 2. Quick sanity check for units. X squared is meters squared. R minus R is meters. So meters squared divided by meters. The units are correct, at least. Okay. So it's not really a, well, it is a quadratic relationship, but it's not a, the units are consistent. So that's good. Right. So of course, and the potential energy. The potential energy V, we use V for potential energy, and it's mgh. So that's mgx squared over 2 r plus r minus r. Right. Now, interestingly, you will see that in the assignment that the potential energy of an oscillator is 1/2 m omega squared x squared. Comparing the two equations, we can write it in a slightly 1/2 m over r minus r x squared. Comparing the two, we can see that this is that. Sometimes using energy is more convenient than using small displacements. So this is another approach of finding omega, because omega is the key parameter of the oscillator. And what we're doing here is we are looking at the energy, and we are seeing that the omega can be established from here. So omega squared is g over r minus r. So time period is 2 pi square root of r minus r g, which looks very familiar, because if you remember, the pendulum equals 2 pi square root of L over G. This is the regular pendulum. And it kind of is. It kind of is, because that's what it does. The center of the ball bounces like this. Center of the ball bounces like this. So it does make sense. Now, please do convince yourself that this formula is true. The potential energy of any oscillator, and that's a general one. It could be it could literally be anything. It could be a mass on a spring, a pendulum, could be the surface of the water. Anything that is capable of performing simple harmonic motion has this equation for potential energy, and that's very useful. And all right. Okay, problem 4. Now this is a classical problem. I love it. I don't remember I don't remember how many times I had to do this when I was in your position. I think at least in the 2 or 3 exams I had the same question, and every time you did it, it just keeps it's just great. Like the feeling you get when you do this question is astonishing. At least for me. I don't know about you. So the premise is that we drill the Earth from pole to pole. That's what we do. That's what you normally do. Obviously, you drill a shaft, and you remove the air, and you drop a stone. Okay. You drop a stone, and the question is, how is it going to move? How is it going to move? What would be happening to the acceleration of the ball as it drops? What do you think? Maybe you already know some formulas that can help you. What would happen to the force? So, Josh, you're saying that the acceleration is increasing. Why? Why would you say? Why do you say it's increasing? True. R does in fact decrease, and it looks like, according to this formula, we would have an acceleration that is increasing in time, and then, but then what happens to the stone at the center of the Earth? Ah, Thomas, yes, you're getting onto something. Of course, we do consider the mass above the stone. So what would happen to the acceleration then? constant. But then what happens at the center? If we let go, right? So it's constant up to which point? So when does constant acceleration become zero? It just makes perfect sense. At the center of the planet, the acceleration would be zero. I don't think anyone would argue with that. The center of the planet acceleration is zero because you're being pulled equally in all directions by the planet. So the acceleration would be zero. But acceleration here is constant. So at which point does constant acceleration become zero? Is it constant up to the center and then suddenly becomes zero and then becomes negative? Any thoughts? What would be a more realistic scenario? I mean, acceleration at the top is g, of course. Acceleration at the top is g. Acceleration at the middle is a. And what is the acceleration at the bottom? Well, it's minus g. It would increase. Adam, you are onto something. You mean SHM? I'm not sure what SHO means, but SHM. Would it increase? But why would it increase, Thomas? Why would it increase? As you go down, there's more and more mass above you. So it seems like the acceleration should be decreasing. And look, it does make perfect sense. And if you draw the graph of acceleration versus displacement, acceleration versus displacement, this is displacement and this is acceleration, you will see that when x is equal to the radius of the planet, acceleration is minus g, and when it's like this, it's minus r. So yeah, it's this, and we know, if I have time, I will prove to you that this is in fact true, considering the planet is uniform. But for now, just believe me that this is true. I mean, acceleration at the center is zero. Acceleration at the bottom is minus g. Acceleration at the top is g, and the x-axis is downwards, of course, because we start from the top. The x-axis is downwards. So when the displacement is r, the acceleration is minus g, and when it's minus r, it's g. We know the acceleration of simple harmonic motion, minus omega squared x. So omega squared is the gradient of that graph, because acceleration is minus omega squared x. So omega minus omega squared is the gradient. So minus omega squared is g over r, is minus g over r. So omega is g over r. Right. And that means we can find the time period. It's 2 pi divided by g, r over g. Yeah, square root. I put the square here. So r over g. So r over g. This is nice. But t is the time period. It's the time period of the oscillation. How long in terms of t will it take to reach the center? How long in terms of t will it take to reach the center? So the stone will perform simple harmonic motion from top to bottom. It will just go back and forth. It's like an oscillator system. Of course, yes, Adam, well done. It's t over 4. So if we start at 0, this is t over 4, then it's t over 2, then it's 3/4 t, and then it's t, finally. Finally, here is t. So it will take t over 4. So the time it takes to reach the center of the planet is going to be t over 4, which is pi over 2 square root of radius of the planet is 6,400,000 divided by 9.81, and 6,004 divided by 9.81 multiplied by pi divided by 2. 1,268 seconds. 1,268 seconds. And the full time period is going to be times 4. 5,074 seconds. Is that realistic? It is independent of the mass of the Earth. The mass of the Earth is considered within g, of course. Yeah, I mean for g you need the mass of the Earth to find g. 5,074 seconds. What's that in minutes? Divided by 60? 84. Oh, yes, it is. It is 84.6 minutes. And now ISS orbital time. Hope you already know the ISS, International Space Station. It orbits the Earth in 90 to 93 minutes. Now, the reason why it's not 84 is because it's 400 kilometers above the ground. It just takes a little bit longer. But in fact, this number, the fact that this number is so close to the International Space Station orbital time is not a coincidence. It takes the same time to travel around the Earth like this at than takes to oscillate like this. Not a coincidence. Uh, let's say low Earth satellite. An orbital period between 84 and 126. So 84 is the lower boundary. Is the lower boundary of a low orbit satellite. They cannot go far. They cannot go faster than 84. 84 is the lower boundary, which is quite interesting. Exactly. Thomas, now you're thinking. Now the problem is, what's the problem with that? If you drop a stone from the ISS, it will continue traveling with the same speed as the ISS, so it will just orbit right next to the ISS. So in order to do that, you have to throw the stone back at 8 kilometers per second. Now, if you can throw stones at 8 kilometers per second, then, well, I assume if you can drill the Earth through the poles, you can throw a stone at 8 kilometers per second, or you have something that can. But yes, so I don't know. Every time I do this problem, it's just so nice. It's just so elegant, and yeah, like and share if you agree. Okay, so what speed will it be traveling? At what speed will it be traveling at the center? Well, I'll try to do an elegant way of that. So because I know that for any simple harmonic motion, x is, well, in fact, x is a sine omega t plus phi. I know that this is true for any simple harmonic motion. And what I need is the maximum speed. So maximum speed is v, but v is the derivative of x. So v is the derivative of x, which is omega a cos omega t plus phi. And at the center of the Earth, the speed is going to be maximum. It's the maximum possible speed, because after that it will decrease. But we know that cosine takes values between 1, -1, and 1. And the maximum value of v occurs when cosine is equal to 1. So v max, and this is a formula you can remember, is omega times a. And in this case, omega is square root of g over r multiplied by the amplitude, but the amplitude is the radius of the planet. So it's going to be square root of gr. And that is square root of 9.81 times 6400000. I think too many zeros. Yes, too many zeros. It's 7,900, roughly 7,900 meters per second. That's the speed the stone will be traveling through the center of the planet, which is about 7.8 kilometers per second. 7.9 kilometers per second, sorry. And of course, of ISS. 7.66 kilometers per second. Oh, not a coincidence as well. 7. It's slightly higher. That's why it doesn't have to travel as fast. But yeah. Right. So you didn't need to use the mass of the planet. It was extra. Now this question was in the physics challenge, the British Olympiad challenge. Although you didn't have to prove this. Now when I did it, I think we had to prove that. And in a way, but basically how you can prove that? Well, if you are here, if you are a distance, let's say r small from the center of the planet, you are not experiencing, so the gravitational force of the ground above you, the gravitational force of the ground below you outside the circle of radius r small cancel out. So standing at this point here, is equivalent to standing on a smaller planet of the same density. So to calculate the acceleration, you just need to consider the gravitational force of the ground that is within the sphere that passes through the point where you are standing. It will take quite a while to prove that, but use that information to try and figure it out for yourselves. Okay, I do recommend doing it. It's quite fun. Look, you can just take as a known fact that you're standing and only the ground below you, only the ground that is closer to the center of the planet than you are, will pull you down. The rest, the gravitational effect of the rest will cancel out. If you wish, you can use integration to prove that, but it is complicated. But then what you need to prove is that G is proportional to X. This is what you really want to prove, because then you prove that it's simple harmonic motion, and if you prove that it's simple harmonic motion, you can use the simple harmonic motion equations. Right. Problem 5. So find the period of small oscillations of the pendulum if the dolly is accelerating at a constant rate A. So you have a dolly and a pendulum, and the dolly is accelerating at a constant rate. Now, what if you've ever been on a, I don't know, roller coaster or any kind of thing that accelerates, you know that standing on an accelerating platform or experiencing gravity are very, very similar. The Einstein's experiment saying that if you are standing in an elevator, if you are in a rocket, if you're in a rocket which is on the Earth, which is just on the surface of the planet, okay, if you're standing on the ground and experiencing gravity, G, arguable that you can ever experience gravity. I don't think anyone can experience gravity. What you experience is the normal reaction force in your feet, but you don't feel gravity itself. You can see the effects of gravity, but yeah. Anyways, if you're standing on the surface of the Earth and acceleration g, or you are deep in space in a rocket and you are accelerating upwards with an acceleration equal to g, and if you're standing on the floor of the rocket, you will not, you won't be able to tell the difference. The experience that the experience you have, the experiences are exactly the same. This is a famous, it is problem 11. No, it is not. It is completely different, actually. Yeah, don't. I use the same picture, but the problem is completely different. It is very, but it is very similar to problem 8 on the assignment, and that's a hint for you. It is very similar to problem 8, just as a simplified version of the same problem. So if you're standing on Earth and there's gravity, or you're standing in a spaceship which is accelerating, the things that you feel and the things that you see around you are exactly the same. And we're going to use that fact. So the fact that the trolley is accelerating and experiencing gravity would be equivalent to the trolley standing still, but experiencing gravity in this direction. Let's call it perceived gravitational field, which would be exactly the same as if there was no g, but the ground and everything was accelerating upwards with acceleration g, and the total acceleration would be this. And if you're accelerating that way, or you're standing on a planet with gravity in this direction, it's exactly the same experience. Now, of course, this is g, and by Pythagoras theorem, we can find the perceived gravity. Perceived gravity is square root of a squared plus g squared. Simple. But then the problem is just turn the problem sideways, like quite literally. Turn the problem sideways. You have a pendulum. You have a pendulum that swings back and forth. A pendulum that swings back and forth. It has a length, and it has the new gravity. So we can write down the time period. The time period is 2 pi L over G, the new G. So it's going to be 2 pi G square root. So it's going to be L squared A squared plus G squared. And it's going to be fourth root of that. That's that. Okay. Does Does this make sense? Give me some comments, maybe questions. G is perceived acceleration. Perceived acceleration. Perceived acceleration. And the trolley will swing around a new equilibrium position, which would be here. Equilibrium position, the ball would swing around this position. Okay. Now, problem 6 is very similar to the problem that you have. Now, so there are two oscillators here. There are two oscillators here. And what's going on? If you imagine what's going to happen when the ball is on a trolley, as the ball moves to the left, the trolley will move to the right. And as the trolley moves to the left, as the ball moves back to the right, the trolley will move back to the left. Because the trolley is free to move, you can imagine that in this position, the trolley experiences a horizontal component to the right, and the ball experiences a horizontal component to the left from the rope. So the rope pulls the trolley to the right and the ball to the left. So the trolley will oscillate and the ball will oscillate. The pendulum would oscillate. And here we remember about the center of mass. They will oscillate around the center of mass. So let's say the center of mass line somewhere here. The center of mass. Center of mass. Now, when the ball will be in the extreme left position, the trolley will move to the right. The trolley will be in an exactly symmetrical position. And look at this. This point will be stationary. This is the stationary point. Great point. So as the trolley swings left and the ball swings right, that point will not move. And because this point will not move, we can consider this pendulum as just being a shorter pendulum. It's just a shorter pendulum of length. Well, let's call it L star. L star is this length. Behaves as a shorter pendulum of length L star. Okay. how do we find L star? Well, we need to find the position of the center of mass. But they say that the oscillation of the ball, the period of the oscillation of the ball is x0, and the amplitude of oscillation of the dolly is y0. So as the pendulum swings to the right, a maximum distance of x0 and y0, y0, it's quite easy to establish that the length of the pendulum is x0 over x0 plus y0 multiplied by L, by the length. I'm going to leave you to prove that, but it's quite obvious from the geometry. It's quite obvious. You need to consider like triangles. So this is y0, this is x0, and we have x0 to y0 is the same as L star to L minus L star. And from here, we can establish that. Yeah. And you can find the time period of the pendulum. Okay, the time period of a pendulum is, oh, you don't need to find the time period of the pendulum. What you need is you might need the maximum speed. So you need omega. And omega, as we already know, is G over L, G over L, G over L star in this case. So it's going to be G over L star, so x0 L multiplied by x0 plus y0. And we know that V max, the maximum speed, is omega times A times the amplitude. So it's omega. So for the maximum speed of the ball, V max is omega A equals omega times x0. We multiply that, so it's going to be square root of g x0 plus y0 over L. Square root of L, that is. And for the V max and the dolly, VD max is omega multiplied by y0. So that is so you know the time period is going to be G y0 x0 plus y0 divided by, oh, it's y0 squared divided by x0 L square root. Yeah, something like that. Just double check. Oh, I don't have it. Anyways, does the last question make sense? The approach that you find a stationary point, and so give me on a scale of 0 to 10, please. Right. Okay. That's great. If you have any questions, do let me know. and hope you enjoy doing the assignments on this topic. Now, yeah. So, any questions? All right, then that's the end of the webinar. So thank you for coming, and I'll see you next week.
Just a question. Is it just a coincidence that the ISS orbits at the same speed as the ball falls?
No, it's not a coincidence. Look, the circular motion and simple harmonic motion are incredibly similar. There are very strong similarities between the two, and you can think of simple harmonic motion as circular motion in one dimension. So if you go around in circles, the x along the x-axis, what you do is you perform simple harmonic motion. So it's not a coincidence, because at the top point, if you're doing circular motion, at the top point, you only have a horizontal component. The horizontal component is equal to your speed, and when at the center, you have the same horizontal component. So no, it's not a coincidence. Topics in year 2. I'm working on it, but mostly it's going to be year 13 stuff. So some of the topics, we have done some of the year 13 topics, but it will be very close to the school program. Yeah, just look, what our aim in general is for you to become problem solvers. We give you we give you real physics problems, because physics is about solving problems. Yeah, and thinking like a physicist means like taking something like and then having an interesting approach, and then finding it. So it's not just about the math. You have to be very creative, and that's what we're trying to achieve, trying to give you. So we're doing the same topics as in school, but with the COMPOS twist. Any year 1 topics? Yes, trigonometry will be there. More differential equations, of course, more integration. So lots of things. Some of the things that we have written this year that were just too big to fit into your assignments. So, for example, some of this assignment has been moved to next year. So we will. So yeah, some of the year 1 topics will come back, but in a different way. It will be completely new assignments. They're not written yet. I have a rough idea of the topics. If there's any topic you particularly would like to do, you can suggest it in the chat. Maybe we'll consider doing an assignment on this topic. We are planning to do some assignments on A-level questions, just to get you prepared better for exams towards the end of year 13. So in general, don't think of COMPOS as something separate from school. I mean, if you do COMPOS and you do it well, you shouldn't have any problems in school, because you've done the same topics but at a much deeper level. So yeah. All right. Welcome. See you.